Sophie Germain was a revolutionary. She battled against the social prejudices of the era and a lack of formal training in order to become a celebrated mathematician. She is best known for her work in number theory, but her work in the theory of elasticity is also very important to mathematics.
Germain was born in Paris on April 1st, 1776. She died in Paris on June 27th, 1831. Things going on in the world. The American Revolution started the year that she was born. The French Revolution began in 1789 when she was 13 years old. Germain was born to a wealthy family. Her dad became a director of the Bank of France. Her interest in math began when she found a book in her dad's library about Archimedes. Legend has it that during the invasion of his city by the Romans, Archimedes was so engrossed in the study of a geometric figure in the sand that he failed to respond to the questioning of a Roman soldier. As a result, he was speared to death. This sparked Sophie's interest. If someone could be so engrossed in a problem as to ignore a soldier and then die for it, the subject must be very interesting. Thus she began her study of mathematics. She taught herself math using books from her father's library, and her parents tried to discourage her learning as much as possible. In the 19th century, it was inappropriate for a female to have such an interest. Sophie began to study at night to hide from her parents, but when they found her books, they took away her clothes, quilts, and light. But none of this stopped her. She wrapped herself in blankets from her bed and lit candles that she stole from around the house in order to continue learning. Her parents eventually realized that her passion for math was incredible, and they agreed to let her learn.
In 1794, when Sophie was 18, the École Polytechnique was founded in Paris. It was an academy founded to train mathematicians and scientists for the country. Women were not allowed to enroll in the academy, but Sophie was able to obtain the lecture notes for several of the courses and study from them. This gave her the opportunity to learn from many of the prominent mathematicians of the day. Sophie was particularly interested in the teachings of J.L. Lagrange. Under the pseudonym of M. Leblanc, who was a former student of Lagrange's, Sophie submitted a paper on analysis to Lagrange at the end of the term. He was quite impressed with the work and wanted to meet the student who had written it. Lagrange was amazed that the work of the author was actually a female, but he recognized her abilities and became her mentor. With a male to introduce her, Sophie could enter the circle of scientists and mathematicians that she never before could. Up until this point, not only had her gender been a hindrance to her, but her social status had been too. It was socially acceptable for aristocratic women to be taught the sciences and mathematics so that they could talk about it casually with friends. Sophie was in the middle class, so this opportunity had passed her by. In 1804, Sophie began corresponding with the German mathematician Carl Friedrich Gauss. She was intrigued with his work in number theory and sent him some of the results of her work in number theory. Again, she used the pseudonym to disguise her true identity. It was not until 1807 that he found out who M. Leblanc truly was. He was thrilled to find that his pen pal was a very gifted woman. In 1808, Germain sent Gauss a letter describing some of her work in number theory. Sophie never heard from him about her last correspondence because he had stopped his work in number theory after taking a job as professor of astronomy at the University of Göttingen. About 12 years later, however, she wrote to the mathematician Legendre about what would be her most important work in number theory. Germain proved that if x, y, and z are integers, and that if x to the fifth power plus y to the fifth power equals z to the fifth power, then either x, y, or z must be divisible by 5. Germain's theorem is a major step towards proving Fermat's last theorem for the case where n equals 5. Fermat's last theorem says that if x, y, and z, and n are integers, then x to the n plus y to the n equals z to the n cannot be solved for any n greater than 2.
Germain actively searched for answers for a general solution for Fermat's last theorem, which states that there is no solution for xn plus yn equals zn if n is an integer greater than 2 and x, y, and z are non-zero integers. She proved the special case in which x, y, z, and n are relatively prime, which meaning they have no common divisor except for 1, and n is a prime smaller than 100. Although she did not publish her work, her result first appeared in 1825 in a supplement for the second edition for Legendre's Theorie des Nombres. She corresponded extensively with Legendre, and her method formed the basis of his proof of the theorem for the case n equals 5. The theorem was proved for all cases by the English mathematician Andrew Wiles in 1995.